Welcome to Mr. Hobbs Pre-AP Chemistry class. This is Thursday, December the 1st. Merry Christmas. Feel free to subscribe to my channel. Alright, today we're going to finish up talking about the periodic table. Yesterday being Tuesday, we started in on talking about the different parts of the periodic table. So when we look up at a periodic table, what is the name of group 1A? Alkali metals. And what does the word alkali mean? Basic, opposite of acid. Okay? So it's not basic meaning simple. It means basic, opposite of acid. pH greater than 7. Because those elements make strong bases. When they combine with the hydroxide ion, the OH minus ion, they make lithium hydroxide, sodium hydroxide, potassium hydroxide. Those are all what we call strong bases. They're the antithesis, they're the opposite of a strong acid like hydrochloric acid or sulfuric acid. So, we have strong acids and strong bases. Those elements make the strong bases, thus the name alkali. The same thing, group 2, alkaline earth metals, same basic name. All right, then when we're inside the goalpost, in the group, what I refer to as the group B elements in there, what do we call all those? Transition metals. And what sublevel is being filled in terms of electrons for the transition metals? The D. That's your D block in the middle there. Okay? Jada said F. Where is the F block going to be? The bottom two rows. And what do we call those elements? The inner transition metals or the rare earth metals. Okay? And then we keep coming over, and then we get the boron, carbon, nitrogen, don't get names. The family 16 are known as CH, chalcogens. Okay? Chalcogens. And then 17, halogens. Okay, like a halogen headlamp, halogen flashlights, they make super bright lights. And then the group 18, noble gases. What are a couple other names? Inert. What does the word inert mean? Inactive, doesn't do anything. Or rare gases because they're found in the air and they're rare amounts in the air. And that's actually how they discovered them, is that you liquefy the air. And when you liquefy a gas by putting it under pressure and cooling it off and getting it super cold, like liquid nitrogen, liquid oxygen are super cold. If any of y'all ever had to have a wart burned off or something at the dermatologist with the liquid nitrogen. Okay? So they liquefy the air, and then they change the temperature and let different gases boil off, and they can collect the gases. And then they found some of the argon and krypton hidden just in very small amounts in the air, and that's how they actually discovered them. So they're called rare gases. But that is a rare name. They very rarely will you hear them called rare gases. They're always going to be called noble gases or inert gases. Now, why are they called noble gases? Why noble? Okay? Did you hear that?
Yep.
What did he say?
He said that they're stuck up and only right with others.
He said, and haughty. That was a good word.
I didn't know what that
So that just means highfalutin. That means that, I think I'm better than you. All right. So that is just the characteristics. And by the way, then row 58 through 71 on the periodic table, the top of the bottom rows are called what? Lanthanides, because it's the first element, 57 is lanthanum. And so then the next row, thorium across, are going to be called actinides. Okay, that they're collectively also known as rare earth metals, and a lot of times you'll hear about rare earth magnets and different things going on with rare earth metals. So if you ever hear that term, they're really talking about 58 through 71. Okay, so that's just all the different parts of the periodic table. Now, I have for you, just looking for me. Here are just some periodic tables. I'm over here.
Hey, can we get one more?
Yeah, that's because I had to type them all in manually, and I got tired of typing them in, and I figured we didn't need to know anything about those. Why is nothing showing up? Okay. So if we're looking at atomic radius, first off, you can even write directly onto this. What is the definition? You need, I don't have any tissue, but you can get paper towel, you can go to the bathroom. Okay? When we say atomic radius, okay, what is that talking about? The size of the atom. So I would even put it right to the side. I left room there so you can put the definition. Atomic radius. Okay? It's the size of the atom. What? Oh, it's looking for me. I'm over here. Here, boy. It's the size of the atom. And it's going to be measured when we have an atom, okay, with the nucleus and the nucleus, it's going to be half the distance between the two nuclei because the electron cloud is real fuzzy. Nope, that's why it wants to be. We don't really know where the edge of the electron cloud is. The Heisenberg uncertainty principle says we don't really even know exactly where the electron is going to be at any given point. So where the electron cloud ends isn't a real defined point. But it's very easy to find where the nuclei are because they're really dense centers. And so they just get the distance between them and they say, okay, well, halfway is going to be the radius of each atom. Okay, so that's just how they find the size of the atom. But atomic radius, the size of the atom. What did we say? What happens to the size of the atom as it goes down? It gets bigger. And why? More energy level. So I would write on here, increases going down. So it increases. And why does it increase? More energy levels. Okay? You're adding new layers to everything, so it's just going to get bigger. Now, what's happened to the size as you go left to right? It gets smaller, so the size decreases. Now, why does it decrease? Okay? Why don't the electrons add any size? Because the electrons are adding size going down. Going across, and by the way, what do we call the rows? Periods, right? We have 1, 2, 3, 4, 5, 6, 7 periods. Okay, that's your rows. What do we call the columns? Groups or families? Why families? Going down, they have similar characteristics, just like people in a family have similar characteristics. And remember, we just number them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so that's your groups or families. So these are your columns. Okay, so as we're going across in a period, we say it decreases. So the electrons are all in the same energy level. Okay, so what does that mean again about size? So they don't affect the size. So they excuse me, don't increase the size of the atom. So what does increase? Why does it get smaller then? Okay? Each new element has an additional proton which pulls the electron cloud in more tightly. Does that make sense to everybody? Okay, so it decreases going left to right, increases going down in terms of size. Let me stand here so everybody can see this. I need to do this right there. I am. All these people that aren't here. Okay, so this first trend is the most important trend. It's the one that, all right, if I pull that down, they won't be able to see my handwriting. Okay? There's just a lot of glare. No, I can't pause it.
No, you can't, but they can.
Oh, yeah. No, I'm just saying it's just there's a lot of glare. I was trying to get rid of the direct on the camera. Okay. That first trend is the one that everything else builds around. Now, if you go down, flip over, and we go to ionization energy. Ionization energy. What is the definition of ionization energy? What's the definition of ionization energy? We started talking about this, didn't we? No? Oh. Okay. So the next one then is ionization energy. What is an ion? A charged particle, a charged atom. And how do we make ions? Take away or add electrons. For ionization energy, it's always going to be the energy needed to take away an electron. The energy needed to remove an electron. Yes, sir. From a gaseous atom, yeah, that's correct. So if we want to add that in, from a gaseous atom. Now, why from a gaseous atom? In the gaseous state, they're going to be individual atoms. So they're not going to be bonded to anything else, so it's just going to be able to, how much energy to take from a single atom. In the gaseous state, that's how we get them to be individual atoms. Okay? And by the way, I did, as you may or may not know, I did share a whole set of notes on this online also. A lot of this is on there, but I think it's still better to kind of write it on the chart and kind of see it. And then you can have it in the notes to kind of go back and look at as well. Okay? So, The ionization energy, the energy needed to remove an electron from a gaseous atom. So what do you think? As it gets bigger, we know it's getting bigger going down now. So what does that mean as far as how much energy it's going to take to remove an electron from francium than it is from hydrogen? It's going to take more or less. Why? That's correct. Why less from francium? What's keeping the electron in the it's in the cloud anyway? That's exactly right, because the farther away it is from the nucleus, that's the thing that's holding it in. The farther away it is from the nucleus, the less tightly held it is. So if it's real close to the nucleus, it's the positive to negative that's holding the electron, the nucleus being positive, the electron being negative. It's that closeness that's holding it in. So the farther away it gets, plus each time you get farther out, you have all these electrons in here blocking and kind of making a negative shield, trying to keep this from feeling that pull of the nucleus. So it's feeling less and less and less of a pull. Even though there are more protons, it's kind of getting blocked by all the inner electrons, all that negative that's between the positive and this outermost electron. So the farther away it gets, the easier it is to remove. Okay? So the less tightly it's held, the less energy it takes to knock it off. So as you go down, so it's this energy, ionization energy, is inversely proportional to the size of the atom. Okay, I'm going to call this IE because I don't like writing it out every time. Okay? So the ionization energy is inversely proportional to the size of the atom. Now what does that mean, inversely proportional? As the size gets bigger, the ionization energy gets smaller. It takes less energy because we're always going to be removing that outermost electron first. Okay? So, ionization energy is inversely proportional to the size. Therefore, okay, what's the trend? As you go down, ionization energy is going to, as the size is getting bigger, the ionization energy is going to decrease. So I would put decrease on this arrow. And therefore, what's going to happen here? Increase. Because it's getting smaller. The electron, the more protons pulling that electron cloud in more tightly, since it's held more tightly, it's going to take more energy to knock it off. Okay? So increase is left to right because the atom's getting smaller. That's why we have to know that first trend, because this trend is totally dependent upon that trend. Now, we can learn about electronic structure from this ionization energy, because the more energy it takes to remove an electron, the more the electron, quote, wants, even though it doesn't have any motions, the more the electron is stable in that arrangement. So things that have high ionization energies means that the electrons are very stable the way they are. Well, as you go across, the noble gases have the highest ionization energy of any element in that period, which means that 8 electrons is the stable arrangement. Okay? So something about having the filled S and the filled P sublevel, S2P6. That's a stable arrangement. These don't react with anything. Helium, neon, argon don't form compounds with anything. They don't even bond with themselves. They just simply float around as individual atoms, and so that means their electron cloud is very stable. They don't need to gain or lose any electrons or share, so they don't bond. Krypton and xenon will form compounds only with the most reactive elements like fluorine and possibly oxygen. But they're very few and far between and very rare. Okay? Radon's radioactive, so it doesn't play well with others, so we don't even talk about it. Okay? So, everything that 8 is very stable. So if we go and look at a chart that looks like this. This is talking about successive ionization energies. So when we're looking right up here at sodium, it takes 495 kilojoules to remove the first electron from sodium. Where's that first electron from sodium being removed from? Which is what sublevel? For sodium, Na, number 11. Which S? 3S, right? So sodium looks like this. With 1 there. Okay? So once sodium loses this 1 electron, it doesn't take hardly much energy at all. 495, it loses this one very easily. Now, it's 2s2, 2p6, right? Now it has 10 electrons, just like neon. It's got the same electron configuration now as neon, the Na plus ion. It's isoelectronic with neon. So now, notice, to take the second electron, now the second electron would be any one of these 6. All 6 of these are, again, that fancy word degenerate. They're equal energy. Any one of these 6 would be the second electron to be removed. Okay, so when we go to try and pull this one out, notice almost 10 times more energy needed to pull this one out than this one. Okay, so that tells me, ooh, there's something stable again about that S2P6. It loses this 1 easily, doesn't want to lose this. So sodium and all the alkali metals, what charge do you think they're going to want to form as far as an ion? Okay, what did he say? Positive 1, right? Y plus 1. You take away an electron, it gets that noble gas configuration. And then to try to take away a second one takes a tremendous amount of energy, so it doesn't lose that one easily, so it'll lose 1 readily. So all of the alkali metals tend to form a plus 1 charge. They tend to lose that S1 electron out there. Lithium will lose the 1 in the 2s, sodium the 1 in the 3s, potassium the 1 in the 4s, rubidium the 1 in the 5s. They all lose that 1, and then after they lose 1, they get the same electron configuration as a noble gas, that stable 8 electrons. Okay? And by the way, we call these electrons that are out here in the outermost energy level. Did we already talk about this? Do we know the name of that electron in the outermost? It's a valence electron. Okay, so if you want to write that down somewhere, valence, V-A-L-E-N-C. Electrons in the outermost energy level. Not sublevel, not just the S or the P, but the whole 3. Okay? So this only has 1 valence electron. It's in group 1, it has 1 valence electron. That's why I kind of like the old school nomenclature with the numbering, because 1A, 2A, and then you come over here to 3A, 4A, 5A, 6A. That group number tells you the number of valence electrons, how many electrons are in that outermost. Now, with the new naming, you just have to use the ones digits. So group 13 has 3 valence electrons. Group 14 has 4 valence electrons. Group 17 has 7 valence electrons. It's really the electrons in the S and P sublevels. Okay? Now, notice magnesium. Magnesium has 12 electrons. Okay? So, it's got 12 protons. Remember, magnesium's a little bit smaller than sodium, right? Because the 12 protons pulls that electron cloud in a little bit more tightly. So it takes a little bit more energy to remove that first electron from magnesium than it does sodium. Okay? But now after it loses one, now the second one takes more because now you're taking something positive away from something negative. Okay? So that makes it a little bit harder. Plus, when these are paired up, there's some electron-electron repulsions in here. They're repelling each other. They're really kind of saying, hey, go ahead, feel free to leave. I want the room by myself. It's kind of like if you have a brother or sister going off to college and you're having to share a room. You know, go ahead, pack. You want me to help you pack? You know, I'm measuring my space here. I got more room for a TV or something. Okay? Yeah. Oh, so he's the one hoping you move out. Yeah. So we have electron-electron repulsion. So when there's two of them, it makes it a little bit easier for the first one to leave. But after the first one's gone, now we don't have that. So the second one's a little bit harder, but not 10 times harder, just kind of a little bit harder, double. But then after we lose two, where's the next one come from? Down here again, right? After it loses two, now what type of configuration does it have? Stable noble gas. After magnesium loses two, it's got 12 electrons to start with. It loses two, now it has 10. Now again, it's isoelectronic with neon, very stable, so it takes a big, huge jump in ionization energy.
So once you get to the noble gas, it stops becoming stable.
Because it's stable. That's the stable arrangement, is that S2P6. So we're going to find that all bonding, all chemical reactions, everything that makes the world go round is because all atoms want to be like the noble gases. Okay? Everybody wants to be like the rich guy. But what type of life are the rich guys living? Single, solitary, lonely lives. Money cannot buy you love. The grass may be greener on the other side of the fence, but the water bill is higher. Yes, ma'am.
Okay, so maybe as like the electrons in the atom are they every time with every element, the atom stops with
When they get to the noble gas, that filled 8.
so
That,
that goes for everything.
well, what happens when you get to the bigger ones? They can't get exactly like a noble gas, and so we have a configuration we call a pseudo noble gas, and I'll explain that in just a second. A pseudo noble gas to where they're still going to lose all their valence electrons, but they can't get rid of all the d electrons, so they get an S2P6D10. All right, but we'll look at that in just a second. So all this is showing is now aluminum. Aluminum has one more electron now out here in the 3p. Aluminum has 3 valence electrons. So after it loses 3 electrons, now we have that big jump again, because it gets the noble gas. So what charge do you think all the alkaline earth metals, what charge are the ions do they form? Plus what? 2, because they want to lose 2 electrons. After they lose 2, then they get that noble gas. What about the aluminum family, the boron aluminum family? They're going to be a plus 3. What about the silicon family? Notice it loses the 4, and then the 5th one is super hard to lose. Now, they really don't want to lose. They're going to end up sharing, but okay. Now, the nonmetals here, they would have to lose 5 or 6. So rather than losing electrons, what do you think they do? Gain electrons, because nitrogen, rather than losing 5, it's easier to gain 3 to get to be like a noble gas. So what would its charge be if it gained 3? Negative 3. The oxygen family, they're going to want to gain 2 electrons to be what charge? Negative 2, because electrons are negative. So if you gain electrons, you're becoming more negative. If you lose electrons, lose negative, you're going to become more positive. You following that? So, if we look up here then on the periodic table, did I really lose it? My other remote had a laser on it. No, it's not that one, the other one. Come here. Okay, so if I look, all of these elements are going to form what charge? Plus positive what? 1. These are all going to be plus 2. These over here are going to be plus 3. These would be plus or minus 4, but almost always plus 4. Okay, but now once you get to that point, they're really going to want to more share than they are lose because they're losing too many. But nitrogen, they're going to want to do what? Gain 3 to become like a noble gas. So what's the charge going to be? Minus 3. Whereas the oxygen family are going to want to gain 2, minus 2, and these are all going to want to be minus 1. The halogens are all minus 1. Noble gas used to be called group 0 because they didn't gain or lose any electrons. Okay? So in terms, we call that the number of electrons it tends to gain or lose, and we're going to find that in covalent bonding share, we call that its oxidation state. Okay? Its oxidation state. And that's defined for you in the notes, and I'll just define it right here. The number of electrons an atom tends to gain, lose, or share when bonding. And that's where you can just write across the top of the periodic table those charges, the plus 1, plus 2, plus 3, plus or minus 4, minus 3, minus 2, minus 1. That's your oxidation states. On the periodic table that I gave to you, the color periodic table, you will see a little black 1 over lithium, sodium, potassium, rubidium, cesium. That's its oxidation state. That means it's forming a plus 1. You'll see for magnesium there's a 2. That means it's forming a plus 2. You see for oxygen, minus 2 and minus 1. It's minus 2 almost all the time when it forms this rare compound called hydrogen peroxide, the stuff you put on your cuts and bobos. Okay? Then it's in a minus 1, but almost always it's minus 2. Okay? When we get into, you'll notice the nonmetals have a bunch of numbers above their symbol. Almost always it's minus 3, minus 2, minus 1. When we get into bonding, we'll see exactly how it can be something else. It's when it's sharing electrons, it's going to share a different amount. When it gains or loses, it's always minus 1, minus 2, minus 3. It's just when it shares in covalent, they can share different numbers, and we'll get there. Okay, so ionization energy. The reason why it's important to study that is because it tells us the stability of electron structures. So it tells us, there's something about that filled S2P6, that noble gas configuration, that's stable. Okay? So we're learning that. So we know that it's inversely proportional. So on our diagram, it decreases going down, increases left to right. So now let's look at the next one on there, which is chemical reactivity. Now, we just said that metals want to lose. The elements on the left side want to lose electrons to get that noble gas configuration. This is very similar to ionization energy. So which ones are going to lose electrons most readily? As you go down in a family, lithium, sodium, potassium, rubidium, cesium, which one is going to lose the electron most easily, most readily? Cesium, because it's bigger, the electron's farther away, right? So it's going to be a more active metal, so your chemical activity is going to increase. Now this is the video that I wanted to show yesterday. Yesterday being Tuesday. I forgot to get it to the right spot. I only want to show a part of it. Yeah. Oops, source. Let's see if I can find what I'm looking for here. Oh, we're playing the DVD. We want to play the video. Stop. We want to play the video.
Indicated a paper on the correlation of the properties and atomic weights of the elements. The substance of this paper is embraced in the following conclusion. 1. The elements of a ray.
This is great 1970s graphics. Okay, that's just talking again, valence electrons right there. Now, hey, this is just kind of cool, this part.
And xenon.
These are your noble gases.
And transparent. Krypton and xenon form compounds only typically. Helium, neon, and argon don't form compounds at all. As we descend the group in the periodic table, the atomic number and the relative atomic mass increases.
So those balloons are each filled with a noble gas.
Helium is lighter than air. Neon is just lighter. Argon and krypton, I've just got to unstick these from the anchorage for a moment. Argon and krypton are both heavier than air. And xenon is the heaviest of the lot. You've heard of a lead balloon? Well, this is it.
Listen. So he's sitting on the side of that building,
Are similar. But
which,
of course,
by the way,
they
is
differ from
identical
one
to
another
Baton
too.
Rouge High and
And
school.
those
I taught
differences
it.
often correspond to some sort of regular change as we go down the group from the top to the bottom.
Yeah, he's totally English. You can tell by his teeth. Okay?
To see these things, let's look at the
Got the
elements
great
of group 1,
polyester pants on,
the
too.
alkali metals. There are 6 alkali metals: lithium, sodium, potassium,
This is
rubidium,
group 1.
cesium, and
That's
francium.
lithium.
They're all soft metals which can be cut with a knife. In air, the
So first thing is true metallic characteristic is that metals are soft. Again, that's why back in the day in the 49ers when the gold rush, you could tell the difference between pyrite, fool's gold, which is hard and brittle, and when you really found gold, the guy would just kind of bite into it. Because if you could make an impression, an indention into it, it was really gold, because gold is soft. That's why we have to add metals to it. We can't use 24 karat pure gold in jewelry because it distorts and bends and won't keep its shape. So you have to add some copper and silver to it to make it an alloy to give it hardness so it'll keep its shape. Okay, so pure metal characteristics are those on the far left. They're soft, malleable, and ductile. Means they can be formed into shapes and drawn into wire. Very soft. Okay, but we're going to be looking at the reactivity of it now. When we talk about that, is how fast does it react? So kind of watch the surface. We're going to show it some oxidation here.
with compounds that form on the metal surface. Here, for example, is lithium. When we slice it, you can see the metallic luster. The black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly.
That's real time. That's not speeded up. It's sped up.
With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster.
So the chemical reactivity is increasing. It's reacting faster.
The elements seem to
Losing
react
its
more
electrons
quickly
to
with
the
air.
air faster.
Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous.
Now realize, this is
All
just
the
putting a
elements
piece
will
of metal
react in
into
the
water.
same way.
It's
Let's
reacting
see
with
an
the
equation
water.
for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge.
So the sodium metal is dissolving
Now
by reacting with the water.
This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame.
Lilac. Okay? Lilac flame. What color is lilac? Purple. Remember we did the flame test and the potassium was kind of gave that purplish color, that violet color in the flame test. And so, do what? That was potassium. So you're putting potassium metal into water. It's chemically reacting with the water, not just dissolving in it, but it's chemically reacting. So the water molecules breaking apart into H plus and OH minus. Hydrogen gas is forming. Now hydrogen gas is extremely flammable. This reaction is putting off enough heat, then the hydrogen gas catches on fire. This is, I don't know if you've ever heard the old classic rock, smoke on the water, fire in the sky. Thank you, you've heard it. Okay? But this gives a whole new relevance to that.
How is it that the electrons in the atoms of this potassium are up? Here it's very cluster. How does it lose the electrons so fast? How does that work?
Just because the electrons are getting farther and farther from the nucleus, there's only one out there. It wants to have that noble gas configuration, and so it just is losing the electron. Oxygen is what we call an electrophile, a lover of electrons, and so that's why things are called. We've talked about. Haven't we already learned Leo goes Gurr? Loss of electrons is oxidation. Gain of electrons is reduction.
Yes, I know that.
So it's called oxidation because oxygen steals electrons so readily from things. So when the potassium's there, it's got the electron, it's ready to give up. Oxygen is coming in there hungry for electrons. Bam, it just takes them away. But you ain't seen nothing yet.
How does
Okay?
when ionization? How does it
Because it's farther away, therefore it's not held as tightly. So it's easier to remove. Long distance relationships are hard to keep.
True.
Okay? Now, hey, so that was potassium. So we've looked at lithium, sodium, potassium. You can see that it's doing the same reaction with the water. It's just getting a little bit more rapid, a little more vigorous. It's terrifying.
Rubidium. This time, we put a safety screen between us and the reaction.
That's rubidium.
You can see that things gradually become more terrifying as we go down the group.
Terrifying.
Let's try cesium, our fifth alkali metal.
Whoa!
And that seems a...
It literally is.
Are they not going to do the thick one?
It literally
Now,
is.
I'll tell you about that one.
fifth alkali metal.
Now, first off, the container. Let me see. I think I can.
How did it? I guess rubidium is very reactive.
Shoot.
Similar elements. That's the most
Try
important.
one more time. I missed it. I was trying to go slow mo. Anyway, that's the container for the rubidium that they threw in there just to react all the last bit in there. Listen at the end. That's the
That seems a convenient
cameraman.
point to break off.
That's a convenient point to break off the study. Okay? So when we're talking about chemical reactivity, we're talking about how fast, how vigorous something reacts. Now there's several things that we can pick up from that video. Number one, as you went down in the family, they all reacted with the water. But because the element's getting bigger and bigger and bigger, and they want to lose electrons, the farther away it is from the nucleus, the easier it is to lose that electron. Okay? So it reacts faster. The chemical reactivity increase. Okay? Now, the second thing that we can pick up from that is the fact that, okay, all those alkali metals react with water. But no other elements really react with water like that. So we talk about the periodic law. Is that when the elements are arranged by increasing atomic, how are they arranged? Increasing atomic, which one? Number. The periodic table is arranged by increasing atomic number.
Because there's a couple of
Okay? So when you arrange the elements by increasing atomic number, the chemical and physical properties of the element repeat themselves every so often. Though. So the periodic law says the chemical and physical properties of an element are a periodic function of their atomic number. So you go, lithium reacts with water, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon don't. Sodium reacts with water. Magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon don't. Potassium reacts with water. And so then the chemical property repeats itself every so often when you arrange the elements by increasing atomic number. Mendeleev arranged it by atomic mass, but there were a couple little irregularities in there. By putting it by atomic number, then that fixed it. So, when we go then back to source, can't see it. When we go back to this, our chemical reactivity, for metals, what happens to activity as we go down? It increases, right? It reacts faster. So then notice here that I have this arrow at the bottom because this is for metals. And if you need to specify metals here, as you go from right to left, what's going to happen to the chemical activity? The reactivity. It's going to increase. So francium is going to be your most active metal.
What would happen with that one?
Yeah, what would happen? Now here's the deal. Somebody asked, why didn't we use francium? Francium, number one, is radioactive. But if you look up here of francium on this radioactive isotopes, and you look at the half-life of francium, okay? Francium is element number 87. If you look where is it? Somewhere right here. Francium 212, half-life of 20 minutes. 222, 14.3 minutes. 223, 21.8 minutes. So that means in an hour, we've gone through 3 half-lives. So after one half-life, however much you have 50% of it. After another 20 minutes, you have 25% of it. So after 1 hour, you have 12.5 grams, or, a very small amount, 12.5% of what you had left. So after 2 hours, you basically have nothing. So francium only exists for a very short time. On the surface of the Earth, there's only going to be a small amount of francium at any given point, and it's only the result of these bigger elements decomposing radioactivity. Okay? But undergoing radioactive decay, they're going to form francium, but then it's going to quickly decay into something else. So you're never going to be able to go and get a big chunk of francium to put in water like that. Now, if you could, it would be highly reactive. It would be an even bigger explosion.
Like this,
Yeah. Okay? But cesium was pretty dramatic. So that's your chemical activity. So for metals, because metals lose electrons, the bigger they are, the faster they lose them. So these are your biggest elements down here. These are your biggest, so they're going to lose the most readily. They're going to be your most chemically active. But what do nonmetals do with electrons? They gain electrons, right? Nitrogen, phosphorus, they want to gain 3. Oxygen family want to gain 2. The halogens want to gain 1. Nonmetals want to gain. So what does that mean? Bigger or smaller are going to be more readily gain them. Which one's going to have a greater attraction for the electron, the big one or the small one? The small one. Remember, the small one holds, has a greater attraction for it. So therefore, the smaller ones are here. Okay? So, no, we exclude the noble gases because they don't bond with anything, so they're not in our chemical activity discussion. So here, the smaller ones are going to be the most active. So for nonmetals, activity increases to the right and increases going up. So fluorine is your most active nonmetal. Francium is your most active metal. Okay? Yes, sir. No, again, noble gases don't react with anything, so we leave those out of the discussion. So we're stopping for chemical activity here. Okay, so I really should have stopped the arrow right there. Okay? So now we have the size of the atom, the atomic radius trend. We have ionization energy trend. We have chemical activity trend. We have one more, electronegativity. Of what? How fast chemicals react. Okay. Now, electronegativity is a tricky one. Wakey, wakey. Oh boy, I just rested my eyes. All right. I feel you. I did not want to get up today. Man, and then this next 2 weeks is going to be rough. It's going to be rougher on you than it is on me, but it's going to be rough. Okay. Electronegativity, big fancy word. I'm just going to say the definition. You're going to write it down. Okay? Electronegativity is an atom's attraction for a shared pair of electrons. An atom's attraction for a shared pair of electrons in a chemical bond. An atom's attraction for a shared pair of electrons in a chemical bond. So, what does that mean? If we have oxygen, oxygen has how many valence electrons? What family is it in? It's in the family 16, right? It's got 4p, but remember the valence electrons, it's going to be 1s, 2s, 2p, okay? 1, 2, 3, 4, 5, 6, 7, 8 electrons. But the valence electrons aren't the outermost sublevel, it's the outermost energy level. So all of these are the valence electrons. So it's going to have 6. It's in family 16, so it has 6 valence electrons. Okay? So the units place tells us the number of valence electrons for any element. So it's got 6 valence electrons. So we represent that, these are called dot structures. We can just put 6 electrons around it. Okay, so it's going to have 2 paired, 2 unpaired. So when it goes in bonds with hydrogen to make water, hydrogen has how many electrons? Hydrogen only has 1. It wants to be like helium and have 2. Oxygen wants to be like neon and have its filled 8. It's octet. So they'll come in and they'll share here and they can share there. So water's always going to form H2O because hydrogen now they're sharing these electrons, so they get to have that filled helium. And oxygen is getting its filled octet to be like neon. So by sharing, they're both satisfying their need to have that noble gas configuration. So the electronegativity then, the bond is that sharing of the pair of electrons between these two. Well, hydrogen is pulling the electrons this way, oxygen is pulling the electrons that way, towards each nucleus. The electronegativity is the atom's attraction for that shared pair of electrons. It's a scale from 0 to 4. 4 being the strongest attraction, 0 being no attraction. In that scale, the metals, in this case, the bigger it is, the less attraction it's going to have. Francium, it has the absolute lowest electronegativity. Electronegativity decreases going down. It increases left to right. Now again, we leave the noble gases off. Fluorine has the highest electronegativity. Fluorine has the highest electronegativity. It's a 4 on the 4-0 scale. Oxygen's number 2. Chlorine's number 3. Nitrogen's number 4. Those are your big 4. Noble gases, again, don't bond. They don't share electrons, so we don't talk about electronegativity with noble gases. So, what does that mean? What does electronegativity do going left to right? It increases. So, fluorine's the most electronegative. It's the most active metal. It has the greatest attraction for electrons. Francium has the least attraction for electrons. Metals lose. Francium's the most active metal. So the two kind of go hand in hand. Okay? It decreases going down, increases left to right. So if you want, just circle on here. This is the highest. This is the biggest, greatest electronegativity. This is the lowest. Francium's is actually, this is a scale from 0 to 4, but francium's 0.7. Now, the periodic table that you have puts fluorine at 3.98, which to 1 sig fig is a 4. Oxygen is 3.44, chlorine is 3.16, nitrogen is 3.04. Then they start dropping underneath that. This is 2.58. Chlorine is 3.16, bromine is 2.96, iodine is 2.66. Those are those electronegativities. Now, you definitely won't have to memorize those. You don't have to be a geek like me. Okay? They're given on the back side of your periodic table. Okay? I know you're just putting that into your phone to make sure that you knew exactly what it was at all times. Okay? Out hunting tonight. Oh, I wonder what the electronegativity of arsenic is. All right. So, those are our trends. Now, those trends are going to be important when we go to the next unit and start talking about bonding. So we're learning the trends so then we can apply the trends next unit on bonding. So that's everything that you need to know, really, for the periodic table. So, now I have for you everything you need to know. It's called a study guide. Thank you, Mr. Montgomery. I'm stealing his stuff. Okay. Huh? We're having a quiz tomorrow on this.
Joy.
Now, you are not going to have any short answer on the quiz tomorrow, but you need to know these concepts. Well, how is the first way? Let's just kind of go through it. We're going to do this study guide together. Okay? Because we're short on time. All right? And I want to give the quiz tomorrow, so I want you to know, make sure you know everything. So, okay? Explain one of the first ways the periodic table is organized. How is the first periodic table organized? By atomic mass. Okay? What's the present periodic law? When you arrange the elements by increasing atomic number, the chemical and physical properties repeat themselves every so often, periodically. But it's when the table's arranged by atomic number. And the periodic law, if you want the actual one, it's in the notes on the first page of the notes that I shared with you. Okay? No, don't go down. Yes, sir. I'm getting there. I'm jumping ahead. Patience. Patience, boy. Okay. So what does make an element stable? What do they all try to get? A noble gas configuration. 8 electrons around the central atom. 8 electrons. That's called a filled octet. Octet for 8. So everything wants to have that 8 electrons. Now, we did number 4. That's a review. We don't have to do that right now. You're not going to have to do this on the quiz. You're going to have to do it on the exam. But that's the noble gas configuration. That's where we put it in the brackets. and then do whatever else outside. Okay? That's actually what's on the periodic table that I gave to you, that noble gas configuration. Okay? Now, define the following and label their trends. Okay? Reactivity, so that's just going through and putting the definitions down. Okay? So I don't really think that we need to work. That's just what we just did. Okay? So now, using the periodic table that's on the bottom and the letters that are at the very bottom of the page, okay? What elements are in period 5? And you can have more than one letter. So period 5, what do you look for to find period 5? Okay? What about rows? You go and find the 5th row. So period 5 is the 5th row. So what elements on the periodic table at the bottom, what elements are in row 5? Okay? I, T, and G. Okay, so you're on the 5th row of the periodic table, right down here at the bottom. You find your 5th row, 1, 2, 3, 4, 5, that's period 5. And what letters are there? I, T, and G. That's your period 5. It's your 5th row. So periods are rows. Is everybody with me on that? So then, which elements are your halogens? Okay, R and F. It's going to be that row 17. Yeah, column 17. That's right. Group 17. Okay, where are your lanthanides? Okay, it's the top row, right? So what letters are lanthanides? Just W, right? What about alkaline earth metals? That's group 2, right? So it's just A. So this is just, again, testing and knowing where everything is on the periodic table, what your family names, your sections. Your noble gases? Just U, right? The very last column. Transition metals. There's going to be several. Okay, so all of these inside the goalpost is what we call it. Stop me if you have any questions. Alkali metals. VKI. And then he's calling them actinoids. This is Mr. Montgomery, the actinoids, but it could be the actinoid, and if you want to put a slash actinides. So your lanthanides and lanthanoids, that's the same thing. I call them lanthanides. That's teacher preference there. So, sublevel S. Which sections are your S sublevel? Your first 2 columns, right? So all the letters in the first 2 columns, that's your S block, your S section of the periodic table. And then go ahead and fill in the P's, D's, and F's. What's the P block? 5 through 10, right? The far right, it's from, look up here on the periodic table up here. It's from 5 boron all the way over to neon 10, that whole section. Remember there can be 6 electrons, so there's 6 columns. Okay, so that's your P section. There's 6 columns, that's your P section. Now, to label all your metals, okay, there's a lot of them. Your metals. Now H would be tough. I'm not going to make you memorize this, but if you look at H, look on the one on the wall. You can see the orange. H is going to be what's classification of this? Metal, non-metal, or metalloid? That's a metalloid. Okay? But Z, that's going to be lead. That actually is 1, 2, 3. It's going to be bismuth. Okay? And so this would still be a metal. So all of these. Now, the thing that I want you to make sure you know on this is that W and V down here, remember they're inner transitions. Those are going to be metals. Okay? So everything to the left side of the periodic table are your metals. So what are your only nonmetals? R, O, and U. And so then your metalloid is H. Okay, so you good with that? Does anybody have any questions on anything we've done so far? That's just kind of knowing the different sections of the periodic table. Now this one's going to start in on some of your trends. Now, we have to... wonder why that K is big. It is potassium right there. I just... okay? I'm trying to think if I did that or not. I don't think I did. Which element is the most reactive non-metal? Now this is based upon, well, what's given here, these letters, but which of these is going to be the most active non-metal? R. Now that happens to be fluorine as well. So that fits for both cases. But which is going to be the most reactive metal? Now which would be the most reactive metal? On the periodic table, where? Bottom left. That would be it. But of the letters that are here, which one's the most reactive? I. So bottom left. So you just do the trend. The farthest to the left and to the bottom is going to be the one that's going to be the most reactive. Okay? Which element below is the least reactive? Yes, sir. Which one?
What's the most reactive metal?
It's going to be I. Okay? Now, B is a good guess. Okay? I've heard 3 answers. Noble gas being U, okay, are going to, all the noble gases are the least reactive. They're the least reactive of everything. What would your questions are? Okay? Yeah, it doesn't say metal or non-metal, so it just says which element. So the noble gases, so this, again, you might want to circle that, you know, it doesn't specify. So noble gases are always your least reactive. But if it did specify least reactive metal, then your least reactive metal is the one at the top and to the farthest to the right. Yes, ma'am, Jasmine. Because it's the top right, because it's the smallest, it's going to have the greatest attraction for electrons. Fluorine, in this video, in the next section of that video, which we'll watch next unit, okay, he talks about fluorine being the Tyrannosaurus Rex of all the elements. It acts oftentimes ferociously with just about everything. Which non-metal would be the least reactive? The ones down at the bottom and farthest to the left. Okay, so something along the lines of like tellurium. Now, because we got to stay on the right-hand side of the zigzag line, okay? But that's not really. We're not going to ask those questions. Yes, sir. It wouldn't be the least reactive. The least reactive one's going to be higher up. So the least reactive one's going to be more like gallium. Even aluminum. Aluminum's not super reactive. That's why it's a good metal. It doesn't react with things. When you're cooking in it, it doesn't react with the food and all that because it's not a very reactive metal. It doesn't oxidize much. Okay? So, which element has the largest radius in period 4? So first off, what does period 4 mean? Fourth row. So we're looking at all of these elements right here. Okay? Now, the largest radius. What happens to size as you go from left to right?
Smaller.
It gets smaller. So the largest one is going to be K, far left. Now this is the largest radius. And then alkali metals, as you move down, what happens to the size? It gets bigger going down, so which element has the largest radius? It's going to be I. So this is how multiple choice questions can get asked on something like this. Okay? Which element has the highest ionization energy in period 4? So 1, 2, 3, 4. Highest ionization energy. Is that going to be the biggest one or the smallest one? The smallest one. Where's the smallest one? Period 4. What happens to size as you go left to right? Okay? It gets smaller left to right. So that means you, and again, the noble gases always have the highest ionization energy of any period. That means they have the most stable arrangement. So it would be U. It's the smallest. If you need to make little notes out to the side of this on why it is that would be helpful. So which element has the second largest atomic number? Now this one's a little bit tricky. So what's happening? What's happening to atomic number? It's increasing, right? So your biggest atomic number is going to be down here. Okay? Now, your second largest. Now the key is that these two rows right here, you got to remember, these two rows fit in right here. Okay? So it might be easier to look up here. So the bottom two rows are going to be your biggest numbers. The bottom row of the bottom two rows. Okay? So, but W is going to be before, what letter is that? E? Okay? W is going to be before E. Okay? And then there's Z way over here. Okay? It's not. It's going to be Z. Okay? Because these two fit in here. So it's going to be W, E, Z, and then V. So V is the highest atomic number, then Z, then E, then W. So the answer for the second highest is going to be Z. Okay? Second highest. Okay? Now which element has the largest atomic mass? The biggest element. Which one of these is the biggest one? V. V, as in Victor. Okay? Now, I like this one. Electron configuration 5s1. This is actually a flashback to last chapter. 5s1. So what row is it on? Well, which row? Fifth. Which section is it in? The first two, and since it's S1, which column is it in? The first one. So 1, 2, 3, 4, 5, S1. Okay? So which one's going to be 7S2, 5F, what letter? Does it say 6? Okay? So 7S, which means it's going to be what row? 1, 2, 3, 4, 5, 6, 7. 7S2, then where's my F section? On the bottom, remember this is going to be 4F, this is 5F. 1, 2, well, he doesn't have that right. It's 6. 1, 2, 3, 4, 5, 6. I was thinking it was 4. Okay, so this is your F section. Remember, this is 4F, this is 5F. So you can just look at 5F6 and say, okay, 4F, 5F, it's in the 6th column, it's down here, it's V. And then last, coming in, which elements will form +1 ions? B, K, and I. Now, I'm not quite sure what he means. Let's leave off 28 and 29. Elements in the same family are all going to have the same properties. Which group of metals will have the same properties? This group? I don't know. I'm not sure what he's meaning on that one. 28 and 29, don't worry about. And then which element in period 6 has the highest electronegativity? Period 6. 1, 2, 3, 4, 5, 6. What happens to electronegativity left to right? It increases, so the answer is going to be Z.
Why is it?
Electronegativity increases left to right.
What's that mean there?
Oh, because it decreases.
Okay, but it says, look, it says in period 6, which means row 6. Okay? So, are y'all comfortable with this? Y'all, the quiz is going to be real similar to this study guide.
I just figure out which process occurs. Ionization and reactivity.
They're the same. When something reacts, it loses electrons.
And then ionization occurs to make it.
Well, ionization is we can just shoot energy at an atom and knock an electron off. When counterreactivity means another atom comes in and pulls the electron off instead. And when atoms react, electrons come out. It's just what's happening. Are we doing it man-made with energy, or is another atom coming in and pulling it away?
If there are more elements, why could there be
Well, one thing. The only the one. Are you saying why when they touch it with the knife does it shiny again? Because they're just scraping off the outer layer. Only the outer layer is reacting with the air. So then they scrape that off, and the next layer can react with the air. And they scrape that off, and the next layer can react with the air. Okay, so you're not making it go back. It's just scraping it off with the knife, and then exposing the next layer that has the reaction. Does that make sense?